Good afternoon, everyone. I'm Anna Stramaglia, and the topic of my presentation of today is Deadlock in packet switching networks. And this is a joint work with Jeroen, Keiren, and Zantema from the Eindhoven University of Technology. So it is known that packet switching networks are not only used in the internet, but also, for example, in hardware devices. And in this context, it is of interest to focus on the concept of deadlock prevention. Indeed, in our work, we focus on deadlock prevention in packet switching networks with a particular interest in networks on chips. So given this introduction and the context of this work, let's see the motivating question of our work, which is the following. So given a packet switching network, can we identify the presence or absence of deadlocks prior to its development? So if, for example, we take into account this packet switching network that is shown in the slide, we see that there are different types of nodes. The pink nodes can send new messages in the network and receive messages from the network, while the gray ones can only forward messages. So given this packet switching network, can we say something about the presence or absence of deadlocks in the phase of analysis with, using formal verification, applying formal verification? So this is our motivating question. Now I would like to introduce then what a packet switching network is. And this is a four tuple composed by a finite set of nodes, finite set of terminals, a finite set of channels, and a routing function. The nodes, we see here an example of four nodes, and I will highlight these normal nodes in this gray color for the presentation. And they are labeled with integers so that we can refer to them. Then there is the set of terminals, which is a subset of the set of nodes. And we indicate these terminals with this pink color. And these are, special nodes because they can send new messages inside the network and consume messages from the network, while the others can only forward messages. Then we have the channels. So a channel connects two nodes, a source node and a target node, and it is identified by its content. So if we write that a channel C is equal to empty, this means that the channel is free. While if we write that C is equal to M, where M is one of the terminals, this means that the channel C contains a message which has destination M, the terminal. In this work, we focus on deterministic routing functions, which are static routing functions, and a function route determines, where to forward, in which channel to forward a message, M, that it is in node N, so that it can receive its destination. We also define what a correct packet switching network is. And a packet switching network is such if every message in the network can reach its destination in a bounded number of steps. And here we indicate this bound with this k greater or equal to 0. Let's see now then which are the possible steps that a packet switching network can take. There are three possible steps. We start with this example of 4 channels, which are all empty, so we are in the initial state, and 4 terminals. And let's now suppose that node 1 wants to send a message to node 3. Then the packet switching network performs a send step, and after it performs this step, we have the channel C1 is now filled in by the value 3. So as I said, the channel is identified by the content of the message, which is its destination. Then node 2 can now, for example, forward this message from channel C1 to channel C2 because C2 is empty. And we have a process step. And after this process step, we see that channel C1 now is made empty and C2 contains the message 3. At this point, we have that the incoming channel to node 3, the terminal, contains indeed the message 3. So node 3 can receive this message. And after this step, this receive step, we have that node 3 has received the message and channel C2 is empty. So we go back to the initial configuration. Another important concept, of course, in this work is the one of deadlock. And deadlock is a well-known bug pattern in computer system, where we have that the system reaches a state in which no operation can progress any further. And in this slide, we have an example of a deadlock situation in a label transition system. So let's see, from the initial state, the label transition system can perform an A action and then a B action, and then it ends up in a state which does not terminate and has no outgoing transition. So this is said to be a deadlock situation for label transition systems. I say that in this work we focus on deadlock prevention, and deadlock prevention stays for the static checking for a packet switching network for deadlock freedom prior to its development. And we find the first approach of deadlock prevention in the field of packet switching network in the 70s. I also say that we have a particular interest on networks on chip, and network on chip, in 2000s brought packet switching networks and deadlock prevention to the level of interconnect networks in integrated circuits. And since these networks are have a static topology, they are amenable to deadlock prevention. And in this context of networks on chip, we see the work of Verbeek-Schmalz in 2010, and they have provided some sufficient and necessary conditions for deadlock freedom in packet switching networks with deterministic routing function. And in our work, well, our approach is able to prove or disprove the presence of deadlocks in packet switching networks, even if those conditions are not satisfied. So let's see now an example of a deadlock situation in this small packet switching network. This is still a packet switching network with 4 channels and 4 terminals. And we see that all of the channels are filled in by a value, by a message, but none of them will be able to reach its destination because every channel is blocked by the next channel. So this is a cycle of blocked channels that cannot progress any further. And this can be seen also in a real-life example, here on the right, as a traffic congestion, where we have flows of cars, and all of them are blocked by the next flow of cars. And so that also in this case, no cars can progress any further. Let's see now, before going to the notions and relations that we have provided about deadlocks in packet switching network, which is the semantics of packet switching networks. And the semantics is defined as the Kripke structure composed by, which is a 4-tuple composed by a set of states, initial states, a transition relation, and a labeling function, over a set of atomic propositions which give the content of the channels. So we have this set of states, and the state is identified by the content of its channels. Then we have the set of initial state, and the state S is said to be an initial state if it contains only 3 channels. Then there is the transition relation, which is the disjoint union of the transitions of type send, process, and receive. So as we saw, these are the 3 possible steps in a packet switching network. And then there is the labeling function, which assigns a set of atomic proposition for each state that it's in the set of states. We indicate with pi over C of S the value in channel C in a state S. And I will give you some other notation. So we also indicate that transition over PR means the union of the transitions of type process and receive, while not transition over PR means that there is no state S prime that can be reached from a state S with a transition of type process or receive. And now I would like to build with you the trace of execution of the example that we saw before about the possible steps. So we start from the initial configuration where all the channels are empty. So we see that the state is identified by the content of these channels. So this is the first state. Then after the send step, we end up in a different configuration where now channel C1 is filled in by the value 3. After the process step, we end up in a configuration where now channel C2 is filled in by the value 3. And after the receive transition, we end up in a state which is the same as the initial configuration. So this is the trace of execution of send, process, and receive step for a message that is sent from node 1 to node 3. Let's see now which are our notions of deadlock that we have defined in this work. I think before introducing these notions, it is of interest to say that this idea of working about defining different notions of deadlock in packet switching network arose from an assignment that was given by Professor Hans Zantema in the University of Eindhoven to a master course. And the students were asked to define and find deadlocks in a packet switching network that was given. And it was interesting to see how different students came up with different ideas of what a deadlock is in the field of packet switching networks. So we thought it was of interest to go deeper into this research. So let's start with the first notion, which is the most general one, and it's the one of global deadlock. And you can think of a global deadlock as a situation in a packet switching network where no transition at all can take place. So the whole packet switching network is blocked. So let's go to the definition. We have that given a packet switching network and its semantics, a state S is said to be a global deadlock state if with a transition is not enabled to reach another state S prime. And we have an example here on the bottom right of the slide. And we see how these 4 channels are all blocked by the next one. So they form a cycle of blocked channels in a standstill situation, which is this global deadlock. And there are no outgoing transitions from a node to another to reach a new state. Then we have our second notion, which is the one of local deadlock. And the intuition behind this notion is that in a packet switching network, that can be the case that only part of the occupied channels are blocked and they will never change their content anymore. And also in this case, we have the definition. So given a packet switching network and its semantics, a local deadlock state in which a channel C is deadlocked is said to be a state S, from which some transitions can take place to reach another state S prime, but the value of the content of channel C will not change and will not change anymore. And we have that the set of local deadlock states is the union of the set of the local deadlock state for particular channel. Also in this case, we have an example. So in this case, you see that the channels from C1 to C4, they are in a local deadlock state. They will never change their content again. But for channel C5, the situation is different. So node 1 can still receive a message from channel C5. So this is not a global deadlock situation, but a local deadlock situation for channels from C1 to C4. Then there is our third notion, when we focus more on the process and receive steps in a packet switching network. And so given the packet switching network and its semantics, a state S that is not an initial state and from which the packet switching network cannot perform a process or receive step to a state S prime is said to be a weak deadlock state. And also in this case, we have an example, and you see that in this configuration of this packet switching network, no process or receive steps are possible. And this is because the channels from C1 to C4 are blocked, as we have seen before, and channel C5 is empty, so no process or receive transitions can be taken here because of the definition of what a process and receive steps are. And you could wonder why node 2 cannot forward the message 3 to channel C5. And this is because of the deterministic routing function that instead would prefer to, choose to send the message 3 to channel C2 in order to reach the destination 3. So let's now see which are the relations between these different notions. And we will start by seeing the relations between global deadlock and local deadlock, and global deadlock and weak deadlock. And these relations come immediately from the definitions of these notions. So given a packet switching network and its semantics, we can state that a global deadlock is a local deadlock and a global deadlock is a weak deadlock. So now that we have shown that having a weak and local deadlock doesn't imply that a global deadlock exists, which is then the relation between weak and local deadlock? Well, we have formalized a theorem, well, two theorems about this, and this is the first one. Let's go to the theorem. So given a correct packet switching network and its semantics, we can state that a weak deadlock is a local deadlock. And the intuition behind the proof of this theorem is that in a weak deadlock state, there exists at least one channel which is non-empty. And since no transitions of type process and receive can be taken because of the definition of a weak deadlock state, any non-empty channel in the packet switching network will never change its content again. And this is the exact definition of what a local deadlock is. About the reverse, we cannot state the same. So we cannot say that a local deadlock is a weak deadlock. And we have a counterexample here on the bottom right. So in this case, as we have seen before, channels from C1 to C4 are a cycle of block channels that will never change their content again. But still, node 1 can receive the message from channel C5. So this is not a weak deadlock situation because a receive step can still be done. And so we have that we cannot say that local is weak deadlock, but there is a weaker condition that holds. And this is in our second theorem. And the condition is that, a weak deadlock can be constructed from a local deadlock. So given a correct packet switching network and its semantics, if in a packet switch network we have that a local deadlock exists, then this implies that also a weak deadlock can be found. And the intuition behind this proof is that in a local deadlock state, let's call it S, part of the occupied channel will never change their content again because of the definition. And it exists a state S prime that can be reached from state S via some transitions of type process and receive. But we have that this number of transitions is bounded because of the correctness of the packet switching network. So that from state S prime, then there are no more process and receive transitions which are enabled. And the channels for which this condition holds, they form a weak deadlock. Here we have an example of how we can construct from a local deadlock situation a weak deadlock one. So we have here the channels from C1 to C4 in a local deadlock state. And if node 1 receives the message from channel C5, then we end up in the configuration on the right, which is a weak deadlock situation where no process and receive steps can be taken. And we already have seen this situation before. So given these notions of deadlock and their relations, we can say that if we want to encode deadlocks in packet switching networks, then we have to be careful because different definitions can lead to, well, subtle differences in what we find. We have also provided in our work...
Sorry, just as promised, this is you are now 20 minutes through your talk.
Okay, thanks. So we have also provided a proof of concept implementation to prove the consistency with of the results with our theory. And this was done by translating packet switching networks in SMB models and using the symbolic model checker NewXMB, which is open source and largely used in academia to find deadlocks in the models or show their absence. So an example of a packet switching network that we have investigated is displayed here on the left. We have this packet switching network with 17 nodes and 27 channels. And we wanted to investigate, you see here on the right, for some set of terminals and each notion of deadlock, their presence or not of these deadlock situations. So we see in this table that there are some cases, and you see here on the column DL, Well, if a D is displayed, this means that a deadlock was found. If it's free, then it wasn't found. So we have some cases where for each notion of deadlock, a deadlock was found for some set of terminals. In other cases, we can ensure deadlock freedom for the packet switching network. And in a third group of cases, we see that a local and weak deadlock are found, but not a global one. And this is also consistent with our theory. About the execution time, I would like to say something about this. So in general, we can say that finding a global deadlock is faster than a local deadlock, and a local deadlock is faster than a weak deadlock. But it really depends on the number of terminals and channels involved in the process of communication. So if we have a configuration where we have a high number of terminals and a high number of channels involved, then the state space also increases and the model check-in time as well, so the execution time. And we have set a timeout of 2.5 hours for the tool. And we see here in the table in the last two elements that the timeout was reached without the tool being able to give an answer to us. I have highlighted this result in this pink color because we will see in the next slide this local deadlock situation. And let's go to this. So we see that for this set of terminals here with the 7 terminals, the channels from node that connects node 11 to 15 and 17, they form a cycle of block channels that will never change their content again. And this is a local deadlock situation. But still you see here, for example, that from node 1, a message can be sent to node 5 or to node 8 and 5 to 8, etc. So this is not a global deadlock situation. And this is indeed what we expected also from the theory. So in conclusion, in this work, we have formalized different notions of packet switching networks, of deadlocks in the field of packet switching networks, namely global, local, and weak deadlock. And we have defined their relations. So we can say that a global deadlock is a local deadlock, and a global deadlock is a weak deadlock. A weak deadlock is a local deadlock, and also a weak deadlock can be constructed from a local deadlock. But we cannot say that if a local and a weak deadlock are found, this implies that a global deadlock will be found for the packet switching network. We have also provided a proof of concept implementation, and we have shown how effectively we can find different types of deadlocks or show their absence. For future work, we plan to generalize this framework to non-deterministic routing functions, still in the field of packet switching networks. Thank you for your attention, and if you have any questions, I will be glad to answer. Thanks.